Okay, wildlife conservationists are concerned that the deer population might not be constant in a 13 square mile area, and yet in a third conservationist counted 216 deer in a 24 square mile plot of the forest. So do the conservationists need to be worried? So the first question is not necessarily mathy as much as it is just thinking, why would we care this? So why does it matter if the deer population is not constant in certain areas of the national forest? So just talking with your group for a minute, why would we care if those deer populations aren't constant throughout the forest? All right, so let's come back together here. So telling me some reasons here. Why might, and there's lots of different reasons why this could be, but why would they care if the deer population wasn't constant in the whole forest? Xavier, what do you think?
Because where there's a least amount of, like, if it's not constant in a least amount of area, or it's not constant at, that means there's a certain area where it tends to die.
Okay, so there might be an area where deer are dying for some reason, and so we want to find out what's going on in that area that's made there be less deer there. What else, Cameron? Okay, so if the deer aren't there, let's expand on that. If they're not going to go out and kill the predators, what might happen to the predators if there's no deer for the predators?
They kill everything else.
What do you think? Well, but what's going to happen? Can you just be like, oh, well, the predators will just kill less? What would happen to the predators? The predators would have no prey. And so, like Cameron went to the extreme there, if the predators have no prey and they starve to death, then the little prey, like the bunnies and everything, are going to take over. They're going to eat all of the grasslands, and then we're not going to have any grasslands. And so Cameron really went to the doom and gloom model there, but it could happen. And in fact, that is something that they found, a true thing that they found about Yellowstone, which is a whole...
It messes up the ecosystem.
Okay. So kind of going off of what Cameron says, it messes up the ecosystem to not have enough deer in one section there. What else? Okay, and just in general, I'm just going to put hunters because it doesn't really tell us what's going on there, but it could be that maybe that area is getting over hunted. Maybe they're not supposed to be hunting there at all, and the lack of deer there tells us that there are people sneaking on there and hunting. Teddy, what else? Exactly. How are we going to round up deer for Christmas? I'm not going to put that down, but that's a valid point. Tyler? Okay, so... Did you just say? Okay, so we might want to know, are the deer moving? And I'm just going to put moving question mark, like why are the deer moving out of this one area into another area? Maybe one area has a whole bunch of deer in it, one area is really low, so we'd want to find out if that's true or not. So if we look at this data that they gave us here, we've got three pieces of data here that we want to look at. We know that there was 144 deer in a 16 square mile area. There were 117 deer in a 3 square mile area and 216 deer in a 24 square mile area. So we want to know the deer population per square mile. If we want to know per 1 square mile, where should square miles be? In our numerator or in our denominator? Xavier?
The bottom.
In the bottom, in the denominator. So I'm going to take my 114 deer.
44.
oops, 144 deer, thank you. And that was a 16 square mile, and that's a way you can write square miles, like miles with the squared. And then we had 117 deer in 13 square miles. And then we had 216 deer in 24 square miles. So with your group, go ahead and find the unit rate for each of those. For 1 square mile, how many deer were there? So, I think most of you found that when you found the unit rate of each one, you should have gotten 9 over 1. So the unit rate of deer per square mile is 9, and the meaning of the unit rate in this problem is in every square mile we would expect to find 9 deer. Now again, it's nature. We're not going to find exactly 9 deer in every square mile, but on average, that is what we would expect to see. Yes? Maybe they did. I don't know how they counted them. Maybe they tagged them. Maybe they made them line up in a big line and then they counted them. I don't know. All right. Okay, so it says use the unit rate of deer per square mile, or remember we talked about that we're always looking at y over x, and again that's something you're going to see about 1,000,000 times more in your math career, to determine how many deer excuse me, there are for every 207 square miles. So if we're looking at y over x, we're saying our unit rate was 9 deer every 1 square mile. So the question here is, if there were 207 square miles, how many deer would we expect to find in that amount of time? And again, we're looking at this, whenever we have a rate now, we always know that that's going to be labeled y over x. So go ahead with your group and solve that. How many deer would we expect to find in 207 square miles? All right. So again, for those of you who have been using unit rate to answer these questions when we're talking about tables and the things that we've been doing, this is going right back into this. That if we have 9 over 1 and we want to get to 207, what do we have to do to 1 to get to 207? Times by 207, multiply by 207. So if I multiply the denominator by 207, in order to keep an equivalent rate or an equivalent ratio, I have to multiply the top by 207. So 9 times 207 is 1,863 deer. All right, so let's look at this one again. The next one says we're going to use that unit rate to determine the number of square miles that we would find 486 deer. So we're still looking at the same thing, y over x, which is 9 deer for every 1 square mile. But now what do I know? Instead of total square miles, what do I know? Total deer. So I need 486 deer. So go ahead with your group and do that work. How would we figure out how many square miles that is for 486 deer? So what am I going to have to do to go between 9 and 486? What do I have to do there? Olivia? Okay, so she took 486 and divided it by 9 and got 54. And what did that tell you then? Okay, 9 times 54 is 486. If I multiply the numerator by 54, I have to multiply the denominator by 54. And so that would be 54 square miles. So it took 54 square miles. I should be able to find 486 deer. So the next thing here that we're going to look at, we're going to do a Freyer model here for that constant of proportionality. Okay, so what we're looking at here, this is constant of proportionality. And the definition here is the constant of proportionality is the number that describes the, big word here, multiplicative. So let's break that down. What do you think multiplicative means? What little word does it have in there that looks familiar? Multiplication or multiply. So we're looking at the number that describes the multiplication relationship between x and y. Yes. Well, you need to know what that is. Like, I wouldn't do it here because you need to know what that word is. Yeah. So when we talk about facts and characteristics there, one of the things that that we're looking at when we talk about that is our unit rate can be our constant of proportionality. When we find a unit rate, for example, on here, we knew there were 9 deer for every when we knew there were 9 deer for every 1 square mile, then that was our unit rate. That was also what we could have multiplied. If I knew how many square miles I needed, I multiplied that by 9, and that told me how much it was. We can also just use a rate, like just the rate. Sometimes it doesn't make sense to go all the way down to a unit rate, but our rate is really still the constant of proportionality. And the other way that we see that is, and we're going to be talking about this more in the next unit, we will see an equation written like that, and that k, that thing that we're multiplying by x to get y, is our constant of proportionality. So lowercase k, and that's how we will see that written. And so that represents our constant of proportionality. So when we look at an example here, let's say that we said something about like for every hour you work, you get $7. Okay? If that was our situation that we had, then our constant of proportionality, our K, would be that rate that you get. You get $7 for every 1 hour. That's our unit rate. But for constant, I shouldn't do that way. Constant of proportionality is more just the number part of it. Okay? We don't need the labels on it necessarily when we're talking about constant of proportionality. When we're putting it in an equation, we're basically talking about the number part of it. So that, it only works on proportional relationships. So let's say we had another example here and we said for every hour you work, you get $7 plus a $10 bonus for showing up. So just for showing up, they give you $10. You get $10 as soon as you come in, and then every hour after that, you're going to get $7. Well, that's not going to be a proportional relationship because on hour 0, you already have $10. So we don't have that 0, 0 to start with. And then if we filled out that chart and we started comparing unit rates, we would not get a constant of proportionality. So when we had our equation there, we could say that this was 7x plus the 10, but then that 7 is not K. That's something else that we're going to learn next year called slope. Slope. But it only works with proportional relationships. And I should have put over here, that would be y equals 7x. Yes, those are slope men up there. Okay, Tom, that he had volunteered to make cookies for his entire grade level. He needs 3 cookies for each of the 96 students in 7th grade. Unfortunately, he needs the cookies the very next day. Brandon and his mother determined that they can fit 36 cookies on 2 cookie sheets. So the first question here, is the number of cookies proportional to the number of cookie sheets used in baking? So what rate was given to me there that talks about cookie sheets and cookies? What do you think, Mark? 36 to 2. So let's make a table here. We're going to make a table. Oops, that's not a very good line. And we're going to have sheets to cookies. So on 2 cookie sheets, how many cookies can he fit on there? Xavier, go to the hall. 36. So if I needed to expand on that, how could I make another point for there? What else could I say? 72. Okay, so 4 and 72. What else? 6. What would I have to do to get to 6 there? Okay. 108? All right. Is that right? Okay. Somebody said what, so I thought maybe he was wrong. All right, so take these 3 data measurements here and then answer that question. Is this a proportional relationship or not? Go ahead with your group and figure that out. Just a number. It doesn't have the labels with it like the rate does. It's exactly the same thing as the rate, but it doesn't have those labels with it. So when we talk about the constant of proportionality here, we would be talking about if our rate was 18 cookies for every 1 sheet, our constant of proportionality would be 18 over 1. Or can we simplify 18 over 1? What's 18 divided by 1? So it could just be 18. Right there. So it says, explain the meaning of the constant of proportionality in this problem. We kind of did that with the rate, but another way to think about it is for every cookie sheet, we can fit 18 cookies on the sheet. So we talked a little bit in that last, well, 2 sections ago when we did our second set on proportional relationships and tables, that another way to talk about that unit rate, or when we talked about, we found the unit rate, is to say we multiply by that same number every time. So we're saying every cookie sheet we have, we can multiply that cookie sheet by 18, and that will tell me how many cookies I can make. So the question here is, if it takes 2 hours to bake 8 sheets of cookies, if Brandon and his mother began baking at 4 p.m., when will they finish baking the cookies? So we know they're getting 18 cookies on 1 sheet. So there's a couple ways that we could approach this. What I'm tempted to do, what I kind of want to do is, I want to know how many, I know they need 3 cookies for each of those 96 kids. So how many total cookies are they going to need if they need 3 cookies for each of the 96 kids? With your group, go ahead and figure that out. Talk about it. How would we know how many total cookies we're going to need? Alright, so how many total cookies are they going to need? 288 cookies. So I need to figure out, how can I go from 18 to 288? What would I have to multiply by there? What? 16. 18 times 16. How did you guys know it was 16? What did you do to figure that out? What could you do?
Multiply 96 and 288 divided by 18 and you get 6.
Okay, 288 divided by 18. I'm sorry. That would have given us that we had to multiply by 16 there. But if we multiply the top and bottom by 16, we get, in order to make those 288 cookies, we're going to have to do 16 sheets of cookies. So that's this is kind of like a 2-part problem, because the next question is, if it takes 2 hours to bake 8 sheets, we need to know how long it's going to take them all together. So we have another rate here. In order to bake 8 sheets of cookies, it's going to take 2 hours. So that's kind of a second part to this, another rate that we've been given. 2 hours to bake 8 sheets of cookies. So how many sheets of cookies did we just say that we are going to have to bake in order to bake all 288 cookies? Yeah. Well, we're going to, That's actually the next lesson that we're going to do on this, is setting that up like that. You could try it and see how it goes, see if you understand it, but there's a few things that we're going to talk about with that one. What do you think?
Okay, well, I actually did this
Uh-huh.
because I found that I did that before.
Okay.
That. So you would divide it by 2, and then you'd get 4 over 1. And then.
Okay, so you found a unit rate first.
Yeah, so
Okay.
the unit rate first, which was
So she found that we could do 4 sheets in 1 hour. Okay, and then what'd you do?
And then after doing the 96 times 3 is 288, and then dividing it by 18 is 16. That'd give you the number of sheets.
Okay,
And
so
then,
how are we going to go from 4 sheets to 16 sheets?
and then you have to multiply, but I divided 16 by 4, and you get 4.
Oops, 4, yeah.
And then you'd have 4 hours.
Okay, so that would take them 4 hours to do 16 sheets, because 4 times 4 is 16. We could have done this up here too. 8 times what is 16?
2.
8 times 2. So we still would have gotten 4 hours. So you could have done that either way, basically. But what we would have found is it was going to take them 4 hours. So if they started at 4 p.m., what time are they going to get finished? 8 p.m., because they're going to have another 4 hours onto that 4 p.m. So 4 p.m. plus 4 hours will give them 8 p.m. So they're going to have to be baking for the next 4 hours to get all 288 cookies done there. They want to prepare crepes for all of the students in their French class. The recipe makes 20 crepes with a certain amount of flour, milk, and 2 eggs. The girls already know they have plenty of flour and milk to make 50 crepes, but they need to determine the number of eggs they will need for the recipe because they are not sure they have enough. Considering the amount of eggs necessary to make crepes, what is the constant of proportionality? So what is our rate there comparing crepes and eggs? Talk in your groups for a minute. What is the rate that they're giving us regarding crepes and eggs? Alright, so come back together here. What is our rate regarding crepes and eggs, Xavier? 20 what? 20 crepes for every 2 eggs. So, but we can reduce that. We want to reduce it if we can. So what can we divide 20 and 2 by? 2. So I'm going to divide the top and bottom by 2. And so 10 crepes for every 1 egg. So when we talk about the constant of proportionality, remember that's just the number now. So 10 over 1, how can I simplify 10 over 1? Just 10. So what does that 10 mean then? How does 10 crepes for every 1 egg. So that constant proportionality means you need 10 crepes for every 1 egg. Or you get 10 crepes for every 1 egg. Sorry. A crepe is kind of like a super, super thin pancake. They usually like wrap fruit around it or something. Like a what? They are really good. They're really good. You get 10 crepes for every 1 egg. Alright. So, knowing that information, knowing our constant of proportionality is 10, then the question is, how many eggs are needed for 50 crepes? So if it took 10 crepes for every 1 egg. What would we have to do to get to 50 crepes? We'd have to times it by 5. For our 1 egg then, we'd have to times it by 5. And we would get, you need 5 eggs. Would be my answer there. Okay, so the big idea on this one that's a little bit different than what we've done before is, first of all, just identifying that constant of proportionality, and then using that. I know that in the past, the other assignments, as long as you were kind of getting that right answer and you could justify your work, but we really want to, on this one, use that constant of proportionality like we did here. Show me what you're multiplying by, because it's not always that one that's a 1 that we're multiplying by on these. It's going to be more often that we have to look at the top number and figure out what are we multiplying by, what are we looking at there.